Welcome to our session, and I'd like to introduce our speaker. Unfortunately, we were not able to have Deepthi AJ show up, unfortunately. So we're going to introduce Dr. Jin Huang. Dr. Jin Huang is a computer science professor at the University of Tennessee, specializing in visualization as a service. He leads the One API Center of Excellence and his research funded by NSF, DOE, DOJ, DOD, and Intel focuses on AI-driven intelligent visualization. His talk is AI Methods for Understanding Implicit Structures in Medical Records. Over to you, Jim.
All right. Thank you for the introduction. So hi, everyone. The talk's title that I submitted was exactly what Sheree said. And then as I worked towards the presentation, I've decided to focus on one very recent paper that we have published. And then it was presented in Europe only this Monday. So this is fresh off the press. And the big premise is how do we do visualization in a storytelling manner, but this time let an AI agent do it. So the official title I want to present in front of you is an explaining agent. So that draws the picture for you that works on the edge. All right, so the agenda would be, I will start with an overview of why we are doing this research, why it's cool, and where are we testing for success. And then talk about specifically the transformer model we built. And then we talk about the application. And then depending on if we have time, I can talk about both the generative use case and the classification use case. If we don't have that much time, we can only we can focus on one, and then in that case, I'll focus on generative, and then I'll show you the results and conclude, talk about the potential for future. So the reason we're doing this is, well, quite simply AI on the edge. And right now, if you look at all of the reports, government agency or industry, one key phrase is knowledge capture and knowledge representation. It is very apt given how AI has transformed lately, and suddenly everyone starts to realize if an AI agent can summarize information, wouldn't that be helpful, right? So then in this case, we want to take it further. We want the AI agent to not only do the knowledge capture, but also draw the picture for you, to explain it for you, right? So now in this case, then we can pose a few example questions to drive the application need. So first question would be, for example, can every medical professional have a personalized assistant? So of course, in the bracket, you can put in anything else. Can someone who is maintaining an airplane? Can someone who is maintaining a critical infrastructure? Can someone who is needing to understand how to navigate through financial crisis, right? So then the second question would be, can they create their own personalized assistant for themselves, right? And then we can take it further. Then can we practically archive a personalized assistant? That's actually not that far-fetched. It is hard to say you're going to use a large language model that is provided by any one of the leading providers. You want to say you archive it. It's far-fetched in that case. But if you can create a personalized assistant on the edge, then you can legitimately ask the question. So can I archive it? Can I keep it? Can I maybe have a different version of it as time evolves? Maybe I want to go back and try to see how last year was different from this year, right? So all of these are enabled by AI on the edge. So then in this case, the test case that we want to show you, and of course, we've been looking at multiple cases. So this one is published, so I'm talking about it. So in medical coding, right? So it is a concept that many people are familiar with, but probably didn't know the details. So I'll walk you through. So consider a patient visits a doctor, right? So in that case, you talk about, hey, here are the complaints, here are all of the things I'm feeling, and here are the tests that can be run. And after that, then there should be some diagnosis. Then in that case, we discuss the treatments. And then after the treatments are discussed, then procedures are done, right? So that's how a doctor's appointment normally pans out. This process has a lot of documentation that come together with it, so medical records. And these documentation reflect a very undirected, unfiltered, authentic process, right? So no one can script how a doctor's visit is. So that's what it is. So very good, real, but messy data. So then the medical documentation does require structure though. So for medical billing purpose, for quality assurance purpose, for care coordination purpose. So all of those depends on structure. So hence medical coding is a key component. It is essentially a process of I want to take whatever is subjectively described, try to standardize it as if a label is sufficient to capture it, right? So we can all say it is not a perfect representation. But overall, it is necessary because it's standardization. It is translation from messy language into clean data. It is trying to summarize. But overall, this is a lossy process. Right? And then in this case, where can AI do a job that humans aren't doing, right? So then let's present this. So you can ask any professional right now inside a hospital, hey, how do we typically code up a medical condition? So for example, sepsis, right? So then based on what we have seen in the research literature, as well as talking to actual people, no one can answer that. So nurses can't answer that. I don't know. I know what I do, but I don't know how my medical unit would do it. A quality assurance officer would not know. I have no idea what's going on in that department. I know what's wrong in the end, but I don't know the process leading towards the wrong problems. And the administrators, so the chief medical officer, have no idea, and so on and so forth. So this is where really I want to encourage the audience to think about this use case. It is not an AI replacing a human being at all. It's really a job that no one wants to do, and let AI do it. Right. So the hard reasons that AI can help is number one, the time pressure. Who has time to read through all of these documents? Right, many of them being imperfect. Cognitive limit. Is the second. So it's essentially needing to be about implicit patterns, to see those, to extract those, to communicate those. Human can do it, but we're not optimized to do so. And lastly, noisy data. So coding is a very imperfect process because it's human done, right? And of course, just want to say there are a lot of AI methods that are being developed or have been developed to standardize the coding practice. So meaning have a machine do it. But we have not seen enough evidence that those work reliably to a point where they're actually adopted. So for the time being, the coding process is imperfect, very, very noisy. So have that be the overall premise. What is the research problem? So the research problem we're focusing on so far is just a diagnosis. So the DX codes. We're not talking about procedures yet because when you have medical records, it's just a lot to look at. So we started with DX, okay, for diagnosis. And in this case, just one thing that we did before building the agent was we want to understand what is the common practice. It is messy. So there are a lot of literature talking about specific guidelines that essentially coding guidelines of how DX codes should be listed, not by temporal order. And by other medical and also clinical / administrative reasons. But DX codes, other than that, can reflect order in which diagnoses were developed. So first you diagnosed A, then you went on to confirm B, and then it's done that way. So it's a mix of not necessarily temporal, not necessarily administrative, but it's a hodgepodge of things. Thereby, it's difficult. And one other thing to add here is medical coding data sets, however you can get them, they are almost never complete in the sense of diagnosis in combination that has never happened before can happen in the future. So in this case, a traditional statistical model is actually insufficient. It is very hard to control, very hard to tune, and it's really not able to learn on its own. So thereby, we want to use the modern approaches such as transformer. All right. So one more example about the codes. So the diagnostic codes literally look like this, right? So on the screen, it is a hierarchical coding system by design. So if you have only one letter S, it could mean injury, poisoning, and all other consequences. But then if you added a letter to it, so S5, for example, it's injury to the elbow and forearm. All right, and you can add one more to it, S5.2, it's a fracture of the forearm. S5.2.5, fracture of the lower end of the radius. 5.2, torus fracture, and then of the right radius, and all the way with the modifier, you can do initial encounter for closed fracture. So not all examples in the big gigantic database will look clean like this, but we picked this to show you that the hierarchical nature is interestingly captured in the sequence. All right. So when you read a code, you can tell a lot about it. And now, so let's talk about the DGPG transformer model that we built from it. So there are two design goals for it. So number one, we want to say, can the transformer automatically learn coding practices? And generally, and this would be applicable to any organization. And number two would be, hey, can we use transformer after it has learned to answer questions and to also visually explain coding practices? All right. So so transformers are good. Well, we looked at other architecture too. So we settled on transformer because transformer are good to really study sequence-to-sequence problems. And so in this case, we have an example of codes. So in this case, on the left, N12 is a particular diagnostic code. And in this case, we're showing an example of a 3-code sequence in medical records. So DX code 1, DX code 2, DX code 3. All right. N12 is the first code. And Q6110 is the second, and 17 is the third. So in this case, then we can already create a sequence-to-sequence training data as on the right. So there is no code in front of it, and then N12 is the next code, right? And in this case, then now we move on to talk about just the first two. So we can easily create a corresponding sequence. And then we can now look at the second two, easily create a corresponding sequence. And then this process can go on. And in essence, this is really what the transformer models are expecting. So it's a rather pain-free process. After realizing how we can frame the problem, this is very mechanical. All right. And so, as I said, a sequence-to-sequence problem is one of the key reasons we chose transformer. But the next one, as I've shown as the example of how the coding scheme is hierarchical in nature, but actually shown as sequence of characters, that's actually great for a transformer model. And in this case, I want to mention one thing. So if there are people in the audience who have used the statistical models to analyze such sequences, graph model is something everybody would typically use. But because of the hierarchical nature of the codes, it's actually extremely hard to find patterns that can hierarchically organize. So in this case, transformer is generated better results. And additionally, the models that we trained and succeeded in using in the end is only 2.5 megabytes in size. So thereby, it really works on the edge, can be easily deployed. And there is no significance in HIPAA compliance and all of those if you give people this transformer model. But if you give anyone the whole data set that you have inside your hospital, you're liable for many, many things. So this is where the knowledge capture and knowledge representation is key. All right, so then the model that we trained is based on Nano GPT. It's inside the GPT 2.0. So we're not doing GPT 3, 3.5, 4.0. In this case, it's really just a transformer model. We use the 3 encoders layers and 3 decoder layers, and 3 attention heads, and the embedding size is 192. And the actual code for the paper is open sourced. The model is released on Hugging Face. So in that case, if anyone wants to try it, I will show the information of the paper so you can follow the paper and find it. And then on the right, we're showing a performance graph of training the model. So the one that's in the middle, the black curve, shows training it literally on a original data set. All right. And then as experiment, just to show order matters. So we tried to take the same original data. We can go literally going and sort the data however we want to, right? So if we sort a third of the records, then there is more ordering inside the data set. And we can also manipulate the data to take any record, randomly shuffle it, right? So in that case, we removed all order. We can do a third of the records, 2/3 of the records, or all of the records. And as you're seeing, order does matter a lot for transformer models. The heavily sorted version of the data set, so ORD 100, we have ordered 100% of the records. It actually works, the model trains really quickly. And then if we randomize the order, the transformer model trends also make progress, but not as fast. It'll take longer to do. So thereby, we're showing you that the order inside the data set is indeed learned. Okay. All right. So the data sets that we tried it on, all of these are public. So if anyone wants to try to repeat how it works, you can obtain the same data set. So MIT has released a MIMIC-4 data set that is obtained from one full hospital in Boston. And the data set is publicly available under a license. So it is not free to download, but you can quite easily get it. And CDC releases 2 data sets, NHCS and NHDS. And these data are also widely available. I want to emphasize one other thing. The CDC data is heavily aggregated, meaning the patterns that they detect in the data set are all real. Only that they are repeatedly happening. So each record in their data set represents many patients. So in the end, so there are only 650,000 different patterns, but it's actually 111 million patient visits. Right. So overall, the data set that actually captures a lot of actual happening. So now let's talk about the fun part with the transformer model. It's not that hard to train, but training process is tricky. But after you figure it out, it's not that, it's rather mechanical. So then we can just by picking data sets, train different transformer models. So here we say the transformer that is trained on the entire combined data set. Transformer that is trained on the entire MIMIC dataset, but MIMIC dataset alone. Transformer trained on the NHCS dataset, and so on and so forth. And then the colored bars here, vertical bars, show how that transformed model, that transformer model trained on the dataset operates on its own, right? So in this case, you can see roughly the loss level is the same. So they perform roughly the same on themselves. But then when you take the that transformer model to apply it onto a data set it has not seen, let's compare the performance. The combined transformer operates pretty well on all, as expected, right? And then the NHDS transformer works really well on itself and itself only, right? So the y-axis on the performance is on log scale. So a difference of this much is very significant. And then the MIMIC data set actually captures quite a bit of a general pattern. So it works well on itself and decent data set it has not seen. So, and in this case, then we are using this as evidence that the transformer model that's built truly depends on the data set is given, which is not a surprise. But this allows many different use cases. For example, a nurse who is in ICU, they may be only caring about how the coding practice for their own unit, right? So in that case, they can quite easily find 1 million medical records in any medical setting. So they can hypothetically say, I want a transformer trained on only our ICU's data, right? Or another one would say, hey, I'm in charge of the hospital, but I want to compare Q1 versus Q2. In that case, simply by dividing up the data set, you can have different transformers that basically remembers the coding practice, and you can give it away, you can keep it, you can compare. And we've also done model size comparison. So in this case, just the same as I would say all language models out there, number of parameters does impact many things. In our case, though, because DX codes is a specific enough use case, we found that the model size, as they vary, the very small one actually performs really well. So we found that the 1.3 million parameter model actually works very close in performance to 11 million parameter model. And from 1.3 million, if you drop it down to 230K parameters, it doesn't work as well. So this is a sweet spot. And then this leads to basically 2.5 megabytes in size. And then the this model is trained using F16 floating points, which is typical as all transformer models out there. So in this case, then we can really hypothesize many things based on such a small size, right? This is smaller than a iPhone picture that you can snap, right? So you pull out your phone, you will take a picture, it's more than this. So the deployability is immense. All right, so I want to jump more to just how can we use the transformer model to visualize. So this is a example for sepsis. And the diagnostic code corresponding specifically to sepsis is A419. And the graph is generated by DGPG, the transformer model, in a generative manner. Essentially, the question the user can ask is, show me the coding practice around A4119. It's sepsis. And then the model will start to generate. So I'll try to generate what comes behind me, what comes behind me further, what comes behind me further. And also the model can be flipped and used to predict the before. Right. So in this case, this is before, this is before, this is before. And this graph, for someone who is not in medical field, needs a little bit of explanation. So, and then I want to show that these come in actual groups. So the first group is the set of acute conditions that typically come before sepsis. And this group is the circulatory metabolic issues that are following sepsis. And the blue group are the actual symptoms and the chronic conditions that are directly related to sepsis. So, as we were talking to users, trying to understand how AI either threatens or helps the human user, one thing that we heard was rather interestingly, have you ever tried to explain to a MD that they did something wrong? It is extremely hard, right? So in that case, let the picture do it. So this is how you can quickly explain that. Let me give another example very quickly. So this is a very rare condition, Ehlers-Danlos syndrome. It is very painful, and it is just not a good situation for the patient. So that diagnostic code is Q796. And then the generative model drew the following picture, where the red are all conditions related to pregnancy and childbirth. So by the time a patient exhibits the symptoms, you have to trace years back all the way from birth. So those are actually usually listed in the medical records as diagnostic codes before that condition. And also the blue are other diverse disease that could come with it. That makes this syndrome a little hard to diagnose. And then the green are the circulatory metabolic diseases related. And then the yellow usually are the health status and personal history codes that also appear in the medical records. So again, this is an agent that can draw a picture that no one has ever seen and help everybody make decisions about it. All right, so in conclusion, I want to talk about a few things. One, DGPG can indeed learn and present knowledge to people, right? So the early work that's published is this work, visualizing medical coding practices using transformer models. It's published on ICP-RAM 2025, and it was presented at the conference this week. All right, and then the key success here is, though, training the DGPG model is time efficient and cost efficient, which offers a lot of options for deployment, fine tuning, version control, and archiving. And it takes about 1,000 seconds on Google Colab to train this model from scratch. So I want to emphasize, if you are fine tuning, it's way faster. But if you train from scratch, it's 1,000 seconds, not that much. And then the total monetary cost is 5 cents per model. So it is highly likely to imagine now that a medical professional, given an AI PC, can train this model locally at their will. I wonder about this collection of records. Can you summarize it for me? I wonder about that collection of medical records. Could you do the same? And that's a very exciting premise. And DGPG model can generate it, visualize, and show how a organization handles a complex task in a highly specialized work settings. So this is a way for me to argue that I don't think the general purpose language model will ever be trained for these purposes because they are niche specific. So it is actually up to the users, the user community, to try to ask the question, how can we have a highly trained model and make it very democratized? Right? So to conclude, we want to say that DGPG has demonstrated one of the first technical feasibility for having personalized AI agent in healthcare. And we're working on other use cases right now. As results become available, we'd be happy to share with the community. All right, that's my talk.
All right, thank you, Dr. Jin Huan, for that excellent talk. My wife has Ehlers-Danlos syndrome, so it was definitely a very personal connection to that. We don't have Q&A for this session, so we're going to move to our next talk, which is going to be a workshop. Alex Sin and Louis Tsai are going to do a hands-on workshop with Gaudi 2 on the Intel Tiber AI Cloud. And so I just wanted to make sure people know that there's only limited spacing for that, but everybody will get a chance to do that workshop going forward. Okay, so see you in the next session. All right, take care. Thank you again.
Thank you.